Hello, everyone. I'm excited to give this internal seminar about some of the research that's been going on in the biomechanics / robotics lab. So my talk today is it's called Balance on the Move, the interminable fight against gravity. And then actually before I go on, I'm gonna move this back because I feel like I'm talking to the slides when I don't have your picture. So, oh, sorry, I don't know what to do with this bar of people. But, okay. Sorry, it's like jumping everywhere. I put it back over here. Okay. So my research vision is to facilitate human mobility. And how I think, there's many different ways that we can facilitate mobility. The way I like to think about it is through legged robots. So what I mean by that is wearable exoskeletons, such as those that could help you if you're gait impaired, you can't walk no longer, can we get you out of the wheelchair and help you walk? Or even gait augmentation, so to be able to carry loads or run faster or walk faster without incurring large costs and energy. So by legs, I do mean wearable systems like wearable exoskeletons. It could also be, for example, robot avatars. If you think there's so many places that we wish we could explore, or even just see if it's stable or not, the condition of a certain environment. Can we send a machine that's as capable as we are, or I guess for its purpose, and act like an avatar for us to go explore new planets or check out the structural stability of maybe after a disaster, for example. So remote exploration is one of them, or inspection. And also I think of robots could be useful as companion robots. So if we think of someone who could go out and go get the groceries for us, or walk out our dogs, things that they could do when we're too busy or unable to do things. But even could be for gait rehabilitation. So if someone perhaps who's elderly, it's best if they walk and move and get out of their home, but there's no one to help them do that. Could a robot be a substitute? So these are kind of the more, I guess, like futuristic thinking of different ways that legged robots can facilitate human mobility. I'm certainly not thinking that legged robots are the solution to everything. There's really depends on the application. But I think in terms of when you think of the world that we've created and allow us to kind of interact the way we do with the terrain, buildings and stairs and that sort of thing, I think legged robots certainly hold some promise for that. So how I plan to facilitate this human mobility is through what I call Bioinspired machine intelligence. So in my lab, I study biomechanics, how people move, how they walk, how they control their balance, for example. So we do human studies. And then I also use that to inform, how can we build better robots that are more mobile, more dynamic moving, more capable. So this could be walking robots or exoskeleton devices. And so what principles can we take from human studies or from the way humans balance and apply that to robots? Likewise, I also think there could be ways we can use robotics to learn more about humans. So maybe, naturally we walk a certain way, but if we were to, put a machine on us or have us move in sort of awkward ways, could we kind of tease out, the different mechanisms behind how we move? So I think robotics also is important in helping us understand humans. So it's not just how can we take inspiration from humans, but also how can we build things to kind of tease out how humans behave and how they balance and interact with the world. So what I mean by taking inspiration from nature, the bio part of biomechanics. So if we take, a person or some movement, one thing we could try to do is mimic their motion. So, what movement they're making and then just copy that. But I don't exactly mean just mimicking motion, because as you can tell, when you just mimic motion, you don't actually know what's going on. What are the forces behind it? Why are they making that motion? So by taking inspiration from nature, I also mean the mechanics. So here I'm just showing the ground reaction forces under the person's foot, but what are the, the interaction with the environment around them, and what kind of forces they're exerting on the ground? What are the mechanics that are involved as people make movement? I also think energetic cost is really important, how we expend our energy, and then how we choose to do it. What are these different considerations of, when we adjust our behavior, how does that affect how much energy we expend or not expend? And of course, that's related to mechanics, not fully understood directly how yet, but so there's some interplay there. But the idea is that, we perform movements a certain way. So what are the underlying reasons for that, and how could that affect the amount of energy we expend to do something? How does that help us choose the way we act? And there's also control. So the control can be bioinspired or derived. So in this example, I just take a soleus muscle, for example. We can take the muscle activity, run it through some processing, and then use that as our signal to, for example, like actuate an exoskeleton. So if I have higher activity, it may be that exoskeleton will provide more force or more torque. So that's one way of looking at control. There's also different methods looking at, for example, some reflexes that we have in human behavior. So there's a lot of, I guess, complications and a lot of intricacies going on and trying to distill things. And so there are many ways that we can take inspiration from human behavior, from biology, that is more than just mimicking motion. So my talk today is mainly focused on the balance control aspect of my lab's research. So the balance control mechanisms to maintain stability during gait. So what is balance control? Well, when you balance, it requires the cooperation of multiple sensory motor processes. And what I mean by that is, we in general can navigate the world without falling every 5 seconds or anything. And then we can even do impressive things such as this person walking or highlining across some sort of chasm, I guess. So, we can be pretty capable of things when we have all our sensory information cooperating with each other. So to do something like this, we would need to understand our body dynamics. So if we move our limb a certain way, we have an expectation of what kind of dynamics it has, kind of like what mass it has and how it should move. We also should be able to integrate our sensory information. So we have our vision, our vestibular system, and our proprioceptive system. So all these tell us about the world, and we have to integrate them together. And then especially if the sensors conflict with each other, how do we decide which one's more accurate than the other? So we have to be able to put that information together in a way that makes sense. And of course, there's also control. So we have to be able to, once we decide where we want to put, our foot, for example, on this slack line, we have to be able to control it to get it there. And it really requires understanding, the dynamics of our body, and also like trusting that our sensors are accurate and that we are going to put our foot there. So these 3 things that are part of balance control really need to work together for us to be able to balance. And so I think in general, you find that it doesn't, walking around maybe to most of us doesn't seem too bad. We can do it with quite ease. But, the problem is no matter what, there's gravity. So gravity plays a part. And then because of gravity, for those who can't walk or can't who don't have good cooperation of these processes, well, then you're prone to falling. So if you can't get all these systems together, they're not cooperating, then of course you're going to fall because the gravity is involved with that. So, and falls are really bad. So in Canada, for example, for older adults, it's the top reason for injury-related hospitalization. I think it's like 70 or 80% of the reasons for someone to be hospitalized related to injuries, and it's because of falls. And then it costs about $2 billion per year to the healthcare system. So it's really particularly bad for older adults. But it doesn't mean that healthy adults that are younger, but older, it's typically defined as 65 years and older. So it doesn't mean that younger adults aren't as likely to fall. So if we had an adverse winter event, like I'm sure in Kingston, you've noticed that the sidewalk can be icy sometimes. It's not really safe. So adults are also 2 times as likely to be hospitalized after these adverse winter events. So falling also has consequences for people who aren't necessarily older. So current research in this area, we can't really tell, we still don't know how to train people or tell people how to balance better. And I think part of it is we don't really understand how we balance. So we have broad ideas of how we balance, but there's still a lot of mysteries about it. So in terms of current research, they can be focused on specific conditions, like a certain pathology, and then you have to do a certain balance test. And these balance tests, especially when performed in clinical settings, or they have to be somewhat simple. So it could be, I don't know, like timing you to get up out of a chair, walk, a couple meters and back. So that would be like a certain test to see if you could do that. That doesn't really tell us maybe if you're at risk of falling necessarily. So it lacks prediction. So maybe it says if you can't get up, then you're probably not really great at balancing. But we don't really know. Can we predict that before that? And we don't really know why. So it lacks predictions. Also, as I mentioned earlier, balance requires multiple mechanisms. So we got the body, sensory, the control. It's not just as simple as standing on one leg, for example, and figuring it out. So when things go wrong, how does that interaction of multiple mechanisms break down? And it could be related to, like if your sensors are conflicting with each other, how do you choose which one to believe? And sometimes maybe you believe something that's a bit noisy than the other. So I think these are some of the reasons why we don't yet know. It's ongoing research how to figure out how people balance, and then how we can train people to be better at balance and reduce the risk of falling. So the goal, which is like the broad umbrella for this talk, is to investigate the underlying mechanisms for maintaining gait stability. So this is one of the research goals in my lab, and we're trying to figure out what people are doing and how we can make balance, translate that into applying them. So some of our key questions, more specifically, are how do humans maintain balance during gait? When we walk, how do we not fall down? How do we contend with perturbations or disturbances? And the other question that's related is how can we translate those principles to assist human balance or controllers for robots? So once we get a sense of what humans do, how can we apply that to help people reduce their fall risk, or to make robots, but to make robots more capable and not also fall every 5 seconds. So for this, traditionally you would go into the lab and you would do a set of experiments. So in a gait lab, you would have cameras and force plates, and you could do in-lab experiments to understand balance. And then from this, you could then understand what are the fundamental principles or the underlying mechanisms for someone walking around in like your artificial terrain, for example. But I think we also need what I call here into the wild studies. So into wild is a term where you do things outside the lab, basically. So in a lab, you can try to construct things that look like outdoors. But once you put all these sensors on people and tell them to walk, are they really going to act like they normally do when they go outside, right? So how do people really bounce? How do they bounce when they go outside? How do they contend with all these different sort of scenarios you might choose, like the sidewalk is uneven, the person's coming, got to avoid the dog on the street or something. So, how do we deal with those different, sort of disturbances? And so I think into the wild studies or going outside the lab is also important to learn about these different fundamental principles, because I think we're missing a component without doing that. And of course, they also have to inform each other. So we have anything we do outside, we have to validate within lab. So if we want to measure, if there's a certain measure of stability we want to use, we have to validate that the sensors that are going to be wearable on the person outside has to actually work or be correlated to what we would do in lab. So after we get these principles, then we can think about how we can apply these to robot controllers. And also assistive technologies, which could be wearable technologies, like to make up exoskeletons, or maybe some sort of sensory feedback system to help people maintain stability. So the 4 projects I'm going to talk about as part of this theme is stability when we're walking at slow walking speeds, and then the into the wild gait measurement system, a wearable obstacle detection system, and then a exo for lateral ankle stabilization. Okay, so in terms of slow walking, it's I don't know, why do I care about walking slowly? We normally don't walk that slowly, but this came about from a previous project where we had an exoskeleton where to control this exoskeleton, we had this neuromuscular controller for it. So what the neuromuscular controller is it's what's called a reflex-based model. I'll explain in a second what that is, but it had 7 virtual muscles per leg. So these virtual muscles had sort of like the simplified dynamics of a muscle. And putting these together, and then by reading the joint angles on the exoskeleton and the foot contact, whether the foot is on or off on the exoskeleton, we can then get joint torques. So then we can say, okay, the knee will move, this torque, for example. Why it's called a reflex model is because when the foot is on the ground, the model will activate, or the control will activate stance reflexes, which is basically my foot's on the ground and I shouldn't collapse on the ground. That would not be helpful if your foot's on the ground and you collapse. So it's to maintain or bear your body weight. And then when your foot's off the ground, you want to be able to swing your leg through. If you're not able to swing your leg through, you're going to hit the ground and trip and fall. So that's why it's called a reflex-based model, because there's these stance reflexes and swing reflexes. And we thought this controller was pretty promising. So there was extensive simulation work done on this by a Hartmut guy and his group. And it seemed it could walk at different speeds, and it was robust to perturbation. So we tested it on individuals with a spinal cord injury wearing a exoskeleton. So this is a video where this subject has an incomplete spinal cord injury, and it's walking with the neuromuscular controller, and it's doing a pretty good job. He's still got crutches because bounce is not solved yet, or actually not even under consideration in this exoskeleton controller. Was able to walk quite comfortably. So then what we did was we put this same controller on a person with complete paraplegia. So the difference is the person on the left can initiate gait, but the person on the right, complete paraplegia, could not initiate gait. And so we wouldn't have the float, what's called a float system, but it's kind of really allows them to move around and but not have them collapse. So it's kind of doing that body weight support. And when we had this, when we put this controller on, we couldn't just use the neuromuscular controller. We had to add position control. We had to actually dictate how the knee and hip trajectories were going to be to initiate gait. So what this person does is he will push a button, and then the exoskeleton will take a step, and then there's a neuromuscular portion of it, but it's not alone. So the reason we had to do this was because this controller also, despite being amazing and can let people walk, it actually can't initiate gait, and it's really terrible at slow speeds, even in simulation. So we weren't really sure why, and so that's how this question of what happens when people walk slow came about. We wanted to kind of look closer into the controller and figure out why it couldn't work. So why is it difficult to generate slow walking? As I mentioned earlier, it's got implications for gait initiation and deceleration. If someone wants to walk an exoskeleton and start and stop, I mean, you should have one that can do that. I mean, the way we solved it in the other one was we had a shared control that would switch between position and neuromuscular. So depending on how far you're away from a correct trajectory, right? Then one or the other would kick in. But still, it's a mystery why this couldn't generate slow walking. And this question evolved into, basically what happens when people walk slowly. So we can't answer why it's difficult without understanding what people do when they walk slowly. And the problem is most studies are done at a sort of faster walking speed of a healthy person, but we don't know what happens when people walk very slowly and what implications that has for mechanics of gait. And this also has implications for impaired walking, or even if for aging. For example, if we look at this plot, so this is a plot of age and median survival, which is predicted median life expectancy by age and gait speed. So the green is the faster speeds down to the red, which is the slower speeds. And so from this plot, you can see that if you walk slowly, you actually have a lower predicted life expectancy. So you know, why does speed have an effect like this? What happens when you're walking slowly? Not really sure, but there are implications for impaired walking and aging. So we wanted to figure out what healthy people do when they're walking slowly to try to tease out then what the implications are for impaired walking or as people age. So just briefly to talk about like the different human walking strategies, the main ones that are talked about are the stepping strategy. So that, I guess these are a bit obvious in the sense that, you know, if someone comes and pushes you out of nowhere, you would probably take a step. So you would take a step, and that's kind of the easiest way to recover. What you can also do is use your ankle or maybe modulate your center of pressure. So if you're standing and you don't want to take a step and so you get a small perturbation, you might use your ankle to sort of balance yourself and regain your balance. If you can't take a step, let's say, and then someone pushes even harder, you probably would kind of lean your trunk forward or, you know, kind of flare your arms maybe at the same time. So this hip or trunk strategy is another method. So in terms of standing balance, usually the ankle is used for small perturbations and the trunk is used for larger perturbations. And then for walking, we normally focus a lot on stepping because, you know, it's something you can easily measure, and it's, you know, why not take a step if you can? So if we look at this sort of top view of somebody walking, so you got the footprints, the dark line is the center of mass, and the lighter gray lines is the center of pressure. So it's where the forces under your foot would act at which it acts. So when we were looking at balance control at slow speeds, we focused on a measure called margin of stability. So this would be the distance between the edge of the foot and what's called the extrapolated center of mass. So you can think of the extrapolated center of mass as a center of mass measure that has position and velocity, because it's not just where you are, but also how fast you're moving that you need to account for. And then here, instead of using the edge of the stance foot, we use the center of pressure as our measure. So what is this, I guess, margin between your extrapolated center of mass and your center of pressure, which is kind of represented by that red arrow there. So margin of stability isn't like a perfect measure, but it is one of the ones we use, that's typically used to look at stability. So we want to see how the margin of stability changes. And I also want to point out that here I have, you know, you're looking at this person walking and they're walking kind of the side profile. So this is more of stability in the walking direction, but we want to look at stability in like the frontal plane and the medial direction, so side to side, because previous studies have found in simulations that your walking direction can be stabilized passively, but laterally it requires active control. So you need some control and to be able to balance that. So what we did was looked at lateral balance control at slow speeds. So this is a plot of kind of the profile of people you're looking from the back as they walk from faster to slower speeds, their trunk, their body, their center of pressure. We know from a previous study that step width for this data set doesn't change. So people aren't doing the stepping strategy here. They're actually maintaining that as they slow down. And this is from, the black is 1 meters per second to the lightest blue is around 0.1 meters per second. So they're going quite slowly. And so as you can see, is the body center mass is there's more lateral excursion, it's moving side to side more, as does the trunk center mass. And you can see that here. So as speed slows, so as you go from darker to lighter color, speed is slowing, and you have more of these excursion, more movement, lateral movement of your body. And so this movement, what does it mean? It could be, well, when I walk slowly, I spend more time on one foot, so I'm kind of leaning over there, so maybe it's just naturally part of the dynamics. Or am I leaning over more because I've lost stability, I need to control it? We're not quite sure, but we're trying to kind of tease out what that means. And then also keep in mind, if you're leaning forward over, you also have to bring yourself back, right? You're not just going to keep leaning forward and fall down. You have to come back and put your other foot down. Trying to see what the implications are having this larger range of motion. What does that mean for stability? So what Aaron did was he looked at this data set and he looked at gait speed and margin of stability, which is the measure I mentioned before between center pressure and the center, extrapolate center mass, so center mass position plus velocity. And in studying this, he found that stability decreased. So as speed slowed, so we're slowing down, so we're going towards zero, stability decreased. And and the reason was, and this is not shown in the graph here, but the reason was because the center pressure excursion was getting larger, and so was the extrapolated center mass, but at different rates. And because the extrapolated center mass was growing more than the center pressure, that brought the stability down. So I think implying in a sense that the ankle alone couldn't fully compensate for this additional motion from the center of mass. So the velocity, center mass velocity is slowing down, but the position is still wider. So the overall effect is it's growing. So we think that, as you slow down, stability decreases. So how does your body, how can you counter that? So then he looked at the joint torques at the minimum margin of stability for the ankle and the hip. And then he found that the ankle and the hip increased in magnitude as speed slowed. And they actually increased at similar rates. So it looks like the hip contributes at similar rates to the ankle. So it seems stability slows down. The ankle alone couldn't compensate, and the hip also jumps in to try to help with compensating. So of course we haven't directly measured like the muscle activity to know if this is true or not, but this is what we could gather from at that moment when you when you're the least stable, it seems like your ankle and hip contribute here, and then actually stepping is not used. So in addition to this, we wanted to gain some further insights from simple models of walking. So when we think of the simplest model of walking, or one of the simplest, can be modeling like an inverted pendulum. So the idea is, as you move through stance, it's like a pendulum rolling over, and then you have your other foot that comes down. And actually, inverted pendulums are the foundation of some walking controllers. So it's not just a simple model, it's actually can be used quite extensively in different ways. So this is just an example of what's called a linear inverted pendulum, and then which is the dashed line, and then kind of the conversion to human-like, well, in this case, they were just playing with step width, but human-like behavior. So we have this foundation. So inverted pendulums can tell us, what insights can we gain from it? We've gained a lot from it. But one of the things it tells us is this pendular exchange. So if we look at the stance period, which is when your foot's on the ground, and you look at kinetic energy and potential energy, it's, as you would expect, where the potential energy would rise as the kinetic energy goes down, and then, just like a pendulum. So there's this exchange, and so what this tells you is during stance or when your foot's on the ground, there's no work needed that you can just kind of fall through. This is kind of an ideal case. So if we were to take this, we can look at perhaps the percent recovery of this exchange. So if kinetic energy and potential energy were perfectly out of phase, then you wouldn't put any energy in. So let's say maybe at some speed there's a peak in recovery. And then related to that, if we look at the work that you would have to put into walking against speed, it should be the opposite. So these are, I don't know what these curves look like. These are just kind of predictions of what they might look like. So then the speed, so the work input would decrease where this percent recovery happens. So presumably at these peaks when the pendulum exchange is most out of phase, there's this like optimal speed where we are most efficient, I guess, in terms of speed. And so this project is what Sydney's looking at this summer. So she's running an optimization to find out how that pendular energy exchange changes as speed slows. And I think it's, in this project, I'm not looking for, so we want to know what happens. It's not so much that I want to identify the optimal speed, but it's more that this exchange comes from dynamics. So the idea is that this pendular motion has some passive dynamics to it. So if this breaks when speed slows, if it's true that it breaks down, what else is going on? What needs to take its place if we can't passively have this, I guess if we can't have this passive dynamic behavior at slow speeds, then what else are we doing to maintain stability? Or what else is part of the dynamics of walking slowly? So, so we're interested in seeing what happens to that exchange as speed slows down. So these experiments were mainly done in the lab, very much lab-based, and this is kind of, I guess, sort of a picture of maybe a typical messy lab would look like you for gait measurement. So you would have some markers that you put on a person, and this particular marker that we use here went wireless, so there's like tape everywhere. But this is like a motion capture markers. Maybe you would have instrumented force plates where you can measure the forces under their feet. We also are measuring this person's metabolic cost, so how much energy they're expending. And you put all these things on people and we're like, okay, walk, and we're gonna figure out like, the mysteries of human locomotion. And I think that works, but are they really enough? So if I take, if I go outside and I'm hiking on this trail and there's like snow and ice and it's narrow and you can't really, for example, decide where to put your foot, what can you do in that case? So how do we, is it enough to measure things in lab? How do we measure the stability that we enact when we're outside and then have to contend with these conditions? So, so I think going outside is really important. And we started trying to develop a prototype system to do this. So this is into the wild gait measurement system. So Phoebe's project was to develop an unintrusive wearable system. So we want to provide physiological data about the user's gait, the balance control, and even maybe their psychological states. So we had person, we want to instrument them with tons of sensors, like maybe like an eye tracker, inertial sensors to look at their movement, GPS to know where they are, pulse sensor for their heart rate, muscle activity, and maybe a load sensor to look at step counts. So we wanted to put all these sensors together. And so her project was to put together a prototype measurement system, and then we chose to use XBs for wireless communication. So she did some preliminary tests. I think the benefit of, I guess, working from home is you can list your siblings to become subjects. So this is a sibling that is helping her with these tests. So she kind of had a mock-up. And so this is a picture of kind of the prototype on and testing this communication between these different sensors. So on the laptop, because we're short power sources, we have, so we have one hook to the laptop. She has a coordinator XB. And this coordinator XB is kind of like the head or the master, I guess, XB. We have the GPS, we have the micro SD that's going to be logging all the data, and the Arduino Uno. And then what she has on the arm is another XB that's a router. So the router will do is take measurements from the pulse sensor and then send it to the coordinator. And we have the pulse sensor for now, but eventually we can add more sensors to it, like the galvanic skin response. So she's got the pulse sensor, and it's going to wirelessly communicate information to the coordinator. And then on the leg, there's the second router, which is has a load sensor on it. If you're FSR, I mean, it's basically a force-sensitive resistor to just not necessarily measure the load, but to know when foot contact has happened. So we have a sensor, a load sensor there. We could perhaps add muscle activity, inertial sensors later. So she's got these two routers that are wireless, and they communicate up to the coordinator, and the coordinator is going to read the data and save it onto an SD card. So from her preliminary test, if we look at this graph, which is of, I'm going to say force, so it's like step counting, and her data points, you can kind of pick out when footfall happens. So this was done at a lower sampling rate, so it's higher now, so that's why it looks a bit choppy here. But she can use the force measurement as a step counter, so we can know when people's foot on the ground or off the ground. She could also, at the same time, because we wanted everything to be synchronized, we don't want to do a synchronization afterwards, so everything should be synchronized. She can also read the heart rate. So the heart rate sensor is a little bit iffy, but it's able to at least read data and send measurements. So I think we'll upgrade that heart rate sensor, but we're able to at the same time read the heart rate and have that sent in. So I think it's a really cool, promising prototype and like a first step to trying to kind of take all the sensors on someone and then bring them outside. So we have trying to develop a prototype for into the wild studies. We have this gait measurement system. Of course, we need to validate it with in-lab experiments to see how if they match up or if there's some sort of translation that's needed done between the wearable sensors versus sort of the standard in-lab sensors. And then hopefully that will tell us more about how people balance outside. And then as I mentioned, we wanted to look into assistive technologies. So if we had this gait measurement system with all these sensors and we can read people, read what they're doing, can we add then real-time feedback and then use that as maybe perhaps like intervention training? So we sort of started on this project with an obstacle detection system. So what this obstacle detection system is, which Lucas worked on, is detecting obstacles in the path and then providing feedback to the user. So if you're walking along, there's an obstacle, you want to be able to sense that it's one there. Of course, we would see it, but if you didn't see it or it was such an obstacle that it may cause you to trip, you'd hope that a sensor could pick it up. So we have a sensor that senses this obstacle and it's going to warn the user. And so what we chose was a toe-mounted LiDAR or time-of-flight sensor that's going to be on the toe. And this sensor is the cone, and then he's partitioned it into 13 sections. So you got a bit of, I guess, resolution in a sense from partitioning this cone into 13 sensors. And what's neat about this sensor is because it's like a cone and you can break it up, you can kind of tell when you've hit, what would be the ground. So that if there was a gap in the road, say you're about to step up a curve, then presumably you'll be able to sense that also through the same sensor. So with this, how this system works is that it detects obstacles during stance. So how it knows that it's during stance is we're using that same FSR or load sensor. So when your foot's on the ground, it says, okay, now you're in stance. So we put that on the ball of the foot. And then during that short period, about half a second or so that your foot's on the ground, it's going to read what's ahead and then figure out if there is a obstacle or not. And if it detects an obstacle, then it will give an auditory feedback. So in this case, it'd be a buzzer. And so what Lucas did, and this is also like amazing at-home examples of prototyping. He took his mock-up and then he put it on a shoe and then he used that to test. So I guess maybe if it wasn't really clear before, these two students were not in Kingston. So a lot of this was done remotely with mailing of like parts and stuff. So it's pretty cool to see how it all came together. So he put his system on a sandal, and this is his first prototype, and then tested it to see how it worked. And then the good thing about having the sensor on the toe is that you didn't have to worry about figuring out, what if it was on a shank, for example, like what angle your shank goes at, that you can do all these calculations during stance and then give a warning if there's an obstacle. So what he did for his test was what he did was he had a room and he was going to step into the room and see if the sensor would detect that there was an obstacle. So in this room in particular, it's a no obstacle condition. So it's a room where there's a wall that's 1900 millimeters away. And he's going to look at the angle, which is, remember I said it broken up into different angles, the cone, and then the distance. And the step is, so the only thing the sensor should read is the wall. And this is what the data looks like from what each angle reads. So this solid line is 1900 millimeters. So you can see the left set of angles red about that distance. Then you have this sort of, I guess, angles, the distance getting smaller and smaller, and that's because of the floor. So there's the cone, and then it sees like the floor, and that's why the distances are dropping there. And then he also placed a small obstacle 500 millimeters away to see if the sensor could detect it. He takes a step in, and then this is the result from that set of experiments. So For this one, this solid line shows you where the 500mm mark is. So you can see most of the angles read that. And then the reason for these that are over that line is because actually the obstacle is small, and so it read over the obstacle. And so from these benchtop tests, it seems like the sensor actually does a really fairly good job of detecting, you know, that there's an obstacle and then where it is and how far away it is. So yeah, so I think this is really promising to, you know, to try to kind of detect where obstacles are and feed them back. And of course, we need to do more tests with multiple humans because, you know, everyone maybe kind of walks differently, hopefully not too much differently, but we want to make sure it's robust to also different walking conditions. So we're looking forward to more tests with the system. So this sensory measurement plus feedback system, I think it's really great because you can integrate it into, say, exoskeletons, robotics for control. So if I sense an obstacle, can I then feed that back into the exoskeleton and say, okay, can the knee flex a bit more because you're about to hit an obstacle? Right? You know, can we integrate that into the system? And so you have your normal controller of being able to handle perturbations, but can we also tell it there's an obstacle and maybe give it, you know, give the knee a bit more flexion? I think what also neat is to integrate with humans. So can we give that sensory feedback and then help people walk differently or give them information so that they can choose to walk, they have the option to walk more stably because they now know that there's something in the way. So in a sense, what I mean by that is, can sensors with haptic feedback restore balance for someone with impaired gait? So if someone has, you know, they walk and they have very low ground clearance and we think they're at risk of falling, can we, you know, tell them, hey, like, can you step your foot up a little higher, you know, to help them walk, for example? So can we use that to help train them or provide them information to walk by lowering their risk of falling? The other aspect, which I think is very interesting is also, is can we use sensors, the sensory system, to improve the gait for healthy subjects or healthy individuals? If we walk a certain way that seems to be optimized, you know, in a way like for lowering your energetic costs, but can we even improve on that? And what I mean is, I think there's like a trade-off between energy and stability. So one example I usually give is to get yourself from upstairs to downstairs, the most energy effective way is kind of like throw yourself, if you don't think about the hospitalization, like you have to throw yourself off, I guess, in that moment, right? But it really is going to incur a lot of expense. So there's a bit of a trade-off, I think, in wanting not to fall and then wanting not to expend a lot of energy. For example, if you were to walk around outside and you really don't want to trip, it's like when you go hiking, you probably walk with like higher ground clearance, but if you're on flat ground, you wouldn't. So I think there's a trade-off that's happening between energy and stability, and I think it'd be interesting to see if we can use sensors to augment the information that people have and see if it kind of forces them, not forces them, but allows them to walk differently, maybe in a more risky way, but that could possibly have some energetic improvement. So I wanted to talk about the last project, which I think is kind of a good kind of use of sensors and robotics together. So this is an ankle stabilization exoskeleton that Harriet's developing. And what it does is it's a brace that tightens when the ankle seems unstable. So we started with just a kind of neat, like a brace from Sport Check, and we kind of hacked into it, or I think as Harriet calls it, Franken brace. And then she added, she mechatronics-ified it. So from this brace, we have these, this motor pulley system. So it will like tighten and loosen the brace. And then she also has, in this picture, this prototype, she has a board where it has a sensor that will sense, in this case it's on the shank, but we'll normally put on the foot, but it tells you the orientation of the foot, and then it records data to the SD card. And the reason we want data to be recorded is, again, we want to verify eventually that this wearable system works like in a lab. So we want to make sure we can record all the information. And so what she was also working on this summer is to sort of, you know, you can't be walking around with big breadboards on you. So she's making a PCB version, so very small board, and then it's going to have IMU, the data SD card for data logging, Bluetooth, and it's going to do the sensory fusion on the board. And so she's making that board, and then we're hoping to integrate that with the motor pulley system and to have it working and be ready to be tested in experiments. So how the brace works is that the IMU monitors the ankle angle, and so if you need your ankle, if it's like wobbling, like you're walking on uneven terrain, or you're about to like roll your ankle, it's monitoring that and trying to see, and this will be like maybe some threshold that could be set. So if you surpass that threshold, and the sensor, and so here I'm using the same sensor, but to detect if the brace is tight or loose. So if that load sensor detects that it's a loose brace, then the motor turns on to tighten the brace. And then the motor will turn off when the load sensor detects that the brace is tight. We're not trying to break people's legs here, so it's got to turn off at some point, so we need to give that information back. And then it goes and loops back. If the threshold is not surpassed, so let's say you were walking on something uneven and then now you're walking flat ground again, but the sensor detects that the brace is tight, then it'll turn on to loosen the brace. And then when it's loose, it'll just turn off, and then kind of loop continues. And of course, the loop is, the flow is actually a little more complex than this, because, you know, if this threshold is surpassed and it's a tight brace, what do you do? So there's actually, it's more complex, but this is kind of the general idea of how this works. And so we're hoping to do more studies and to verify how this works on uneven terrain in the injury labs and also outside. So just to summarize, so I talked a lot about the research going on in my lab about balance control mechanisms to maintain stability during gait. Some of the takeaways of this are, I think the trunk is important for balance control, especially when stepping is limited or not used. So even though we use stepping to help us balance, I think that there's a lot we can learn from how we use the trunk, especially in situations where we can't put our foot where we want to. Exoskeleton controllers based on healthy walking speeds may be inadequate. So a lot of case studies revolves around healthy, normal speeds, normal people, but we need to know what happens when people walk slowly, because that might give us insights on how to make better exoskeleton controllers. So if you think there's no exoskeleton that that can walk really fast, and there's many reasons for that, but I think it'd be good to understand how healthy humans balance at slow speeds, and then how can we translate that to exoskeleton controllers. So in terms of the one I mentioned earlier, the way the controller scales the torques is not appropriate, I think, to the way what actually happens at slow speeds. And also there's no balance in that controller too. I also think we can't fully study gait stability without going outside. I think we can do a lot in the lab, and I definitely think there should be a combination of the two, but I think it's time with all the especially technologies of inertial sensors and other wearable sensors that we can maybe start thinking about going outside. And also, this is more of just kind of a thinking about the summer, but that remote hardware development is somewhat possible. So I say somewhat because, if you notice, most of the projects dealt with sensors, so it's kind of just sending components back and forth. It's harder when you have motors and you have to maybe send a power supply through, but it's definitely possible, and I was really happy with the just seeing all the cool hardware development happening on the other side of the computer screen. So why this is important, just as a reminder, like, why am I talking about humans and human strategies? I really want to think about how to augment human mobility, how we can do that with assistive technologies and robot controllers through wearable systems, exoskeletons. In terms of like current, I guess, state of the art, a lot of the exoskeletons and robot controllers do a lot with stepping, like where to put their foot, but less so on the ankle and the hip. Actually, most exos don't even have a motor at the ankle, and they don't do much with the trunk. So it's not surprising that for exoskeletons, there's currently we need crutches in order to walk. And then for robot controllers, there's beginning to look at trunk strategies, but a lot of it's still relying on stepping in place. And then, of course, we got robots falling. So I think there's a lot of, I wanted to kind of talk about a little bit about collaborative opportunities, I think, between my research and researchers at Ingenuity Labs. It's just kind of different ideas, like some of these could be used for intervention or balance training for elderly or impaired, like we could have haptic feedback in a virtual reality environment. You know, what haptic modality is best for this, I don't know. So we use auditory in this case, but it could be vibro-tactile, for example. In terms of gait stability, we've employed more traditional techniques, but as we gain more data from going outside, it might be too complex, so we might need some machine learning techniques. So terrain obstacle mapping could be important when we start to look at where humans are versus what the world looks like. And then any sort of interactions with humans, even exoskeletons, prosthetics, legged robots, and also any sort of outreach or maker-style robotics. Big fan of that. And then I'm also interested in, just kind of put this out there if anyone else is, I'm thinking of trying to get a Spot robot. So Spot is a robot from Boston Dynamics. It's kind of a state-of-the-art quadrupedal robot. It's kind of employed in they've had a leasing program for a while, and now they're starting to sell it in the US, and they're going to sell it in Canada. So I think it'd be good for remote human-robot interaction, remote mapping and inspection. It's not good if you want to modulate its gait, so I can't actually go into the gait controller and modify that, but I think for human-robot interaction and any sort of mapping inspection, I think is important. So if anyone out there has a, I don't know, like a discovery grant that's related to, that you think this Spot robot could be useful for, let me know. So they get to the point where you can control it with like a remote control, you know, like a game, so it's kind of pretty easy to do. So yeah, so I want to end on thanking my students for all their hard work. So the picture, this was inspired by Ali's picture. I was like, oh, I need a picture of my lab because I always forget to do so. But yeah, it was really great work they did over the summer, especially to the summer students who, you know, I really want to, and I think a lot of professors can relate. We really wanted to give them like a good research experience. But of course we couldn't be in the lab space, but I was really very happy with how the summer was, and I'm really happy to have everyone in the lab. So yeah, and that's it. That's my summary. So, thanks.